Thank you. Thank you, Richard. Pleasure to be here. I remember those dark ages. I was thinking about that the other night. What did you have? It was an AT, a computer, wasn't it? It wasn't even a 286 yet in the back of your van there. And I remember, too, you and Jack Newton and I, in a field in Ohio, had to sign a contract promising we wouldn't copy the software that this guy gave us. It was called PhotoStyler, which is the precursor of Photoshop. And that was the first time we were actually able to put red, green, and blues together and make a color image. You did it on my computer, I remember, and it was Jupiter in color. Wow, cool. So we've come a long way. And thousands of dollars later, as my wife will say. Anyway, we're going to talk about high-resolution imaging, digital imaging of the planets. And Bob Gendler is a tough act to follow. He made one very good point, and I think this is, kind of our theme song, is that you're never satisfied when you do CCD imaging. And he certainly showed that today with his talk, and I think in planetary work it's the same thing. You know, I do an image of Jupiter or Mars, and I say, oh, this is great, this is the best I've ever done. And Damien Peach the next day sends me one from England, which, yeah. And so you're constantly, you're going. It's not a competition or a challenge, but it's definitely, I think the good mentality to have is that you're never really satisfied with your work because it can always get better no matter how good it is. Anyway, the digital imaging, I'll just go through this very quickly here. You have a linear response. That's one of the big advantages of that over film. And no reciprocity failure, which means that you're, in general, the longer you expose, you will get the signal will increase directly with the exposure and not fall off like it does with film. And you get instant gratification, which is kind of neat. Because when I was doing film photography, and I know most of you who have done that, you have to spend hours and hours in a dark room or send it to a photo lab, and it's generally a day or 2 or 3 days before you see any result, and then you realize that, oh my God, the shutter was closed. You know, I mean, this has happened. So here you at least know if you mess up, you know right away you did, and you can redo it. And the key to this in planetary imaging is that you get shorter exposures, and this is really, really important. Now, this is what Richard told me when I got that Lynx camera. It was a little different story, Richard, because I bought the Lynx. I took it out of the box, and I plugged it in, and, you know, it just didn't plug into the computer. You had a circuit board this size that you had to shove into the slots in your computer. And then you run a long cable going to the camera. And I used it, and it worked. And it sat in the box for 4 months until you came to the house. Because I was afraid to use it. I had no idea what this camera was doing. And Richard said, hey, there's no sweat. It's the same as film photography. And it really is. If you look at it from that point of view, of course, many of you now have never done film photography. Well, the younger people, you know, it's film. But basically, you know, it's the same principles, and that's kind of what we go by. And there are 2 main principles that you use in film photography or any kind of imaging, is that the image size, and that's the size of the image on the sensor, is directly proportional to the focal length of your optical system. And we call it effective focal length, or EFL, because we get to change it a lot. And the exposure is directly proportional to the square of the focal ratio. Focal ratio being the diameter of your objective divided by its focal length. And it's the same as in film, using little lenses on cameras or big monster telescopes. Now, I'm going to get through the really boring and repulsive stuff first, so we don't have to, you know, worry about it. But basically, the image size, remember we said, is proportional to the effective focal length. That means you had a C8 8-inch f10 with an 80-inch focal length, and you have a 20-inch f4 with an 80-inch focal length, and you take an image of Mars or Jupiter. They're going to be exactly the same size on the sensor at the focus. Okay, it doesn't make any difference. You can go to Kmart and get a Tasco 2-inch f300. Oh, show the craters on the moon. Or you can go to Palomar and have a 200-inch f3 and have the same image size. Now the difference is that the smaller telescope will need much longer exposure because the exposure varies with the square of the focal ratio. In the 8-inch f10, that's 10 squared is 100. The 20-inch f4 is 16, so 16 goes into 106.25 times, and that's how much you got to increase your exposure. So with that in mind, that's kind of just the only things you really have to remember as far as doing any kind of imaging. And again, Richard mentioned, you really helped me on this talk because, you know, I'd forgotten this stuff. He mentioned that the Lynx camera had the 192 by, what, 164 something chip, little bitty chip. And everybody said, well, you know, that's not going to work. I mean, you just don't, you got to have a big, you know, big piece of sensor here for this. A little bitty chip isn't going to work. And Richard said, no. He said, it'll work because we're going to match the size of the image to the sensor. And he coined the term, we don't have pixel envy in planetary imaging. So this is exactly what we do. We can now get by with a much smaller image size than we would with a like normal film. We need less focal length, therefore the focal ratio is lower. Every time we cut the focal length in half, we decrease the exposure by a factor of 4, and less exposure time. And what does that mean? That means we beat the seeing, okay? And this is the key to this. These cameras aren't any faster than film. Ektachrome 160 and the Lynx camera probably had the same ISO or ASA speed. But the thing is that we don't need such a big image with the CCD chips as we did with film to bring out the same detail. And that's where we really win. We beat the seeing, and living in South Florida, we've had some rather poor seeing lately with Hurricane Wilma. And this is next one is a view of my observatory. That's you know, bad. And this year, however, we're probably going to get more hurricanes, and so I'm determined to go out during the eye and actually test the seeing, you know, quantitatively. And a couple of professional astronomers said that they would publish this posthumously, most likely, but they will publish it. So that's good. Okay, this is a true, in my experience, thing of exposure times in seconds on Jupiter using film, a CCD camera, or a webcam. And you can see the CCDs and webcams, you're a whole lot better as far as short exposures and therefore beating this atmospheric turbulence that plagues planetary astronomers. Now, for years it has been an axiom that the visual observer of a planet or moon, extended object like that, will really see much more detail than you could possibly record on film. And that was generally true because film, as you see here, we're talking several seconds exposure time on film to have an image scale big enough to record anything. Well, you got maybe a tenth or a 20th of a second of really good seeing. The eye can pick that up. It can integrate that. It can record it. But the film can't, because then you got all the other seconds of really kind of crummy seeing, and it averages them together. So this has always been an axiom. Well, this is now no longer the case, because with CCD revolution, especially with webcams, we're now dealing with exposures that are about what the eye can see. A 30th of a second, a 60th of a second sometimes, even a half a second. And we can pick up these moments of good seeing and get nice results. And the key is, again, the lower focal ratios we need, shorter exposures. This is a picture of Mars I did back in, I don't know, in the 80s. And it was another axiom that Mars, under 8 arc seconds, you really couldn't get any decent pictures. And the reason is you were using, again, film, you're using a large scale, and the under 8 arc seconds, any variation in the atmospheric seeing will just distort the image. And you can see here, this is my best effort on a small planet size on Mars. And nothing to write home about, but it does have data. So we went then to, this was 5-second exposure at f120, just to get that size on the film. Okay, now we go to CCDs, and Mark Manner is one of our ALPO observers. This is at f40 using a webcam, LuCam here, and Mars is a little under 5 arc seconds. I mean, those are good pictures. Doing a picture like that at opposition of Mars back in the 1970s and 80s would have been an award winner. Literally, that would have been right in the sky and telescope. And now we're doing 5 arc seconds. This is Christophe Pellier over in France, and here's, again, these were just taken a few days ago. He's using f65, but again, look at that. Mars is 5 arc seconds. One of our observers, in fact, Joe Ulowitz, was, I don't know if Joe's here, but there you are. What, yesterday, I didn't show you a picture, but yesterday, that's because my brain isn't working anymore. You know, you get old, things happen. If it weren't for flashbacks, I wouldn't have any memory at all. But Anyway, you took one yesterday, right? Just before you came here. Mars is what, 4.7 arc seconds. And so, I mean, you know, we're breaking every year, every day, we're breaking new boundaries. And Joe is in Northbrook, Illinois, which is where I used to, right near where I grew up, and using an 8-inch telescope, Newtonian. So it's just really amazing what's happening. Here we can see we're now going for the satellites of the giant planets. The imaging of planets is no longer fun, so we'll do Ganymede and just process and blow it up and see real surface features on Ganymede. Here's a nice shot of Jupiter, which, well, it's not great. I took it a couple weeks ago. And there's Io casting a shadow, and you blow that up, and you can see Io looks like a little dash. You say, well, it's because, you know, the drive wasn't working. Yeah, well, of course, that's not true. Io really is a little dash because its poles are dark. And it does look like that. You can see the whole moon right there. Now, I haven't got the volcano yet. That's next year, I'm sure. Damien or somebody will come up with a shot of a volcano erupting on Io. You know, no question. This is Damien Peach's partner over in England. They just got back from Barbados. I hate them with all the fiber of my being. With a C-14. And, but it just shows the kind of the quality work. I mean, this is spacecraft type of work these guys are doing. We have a new feature on Jupiter called the Little Red Spot. Red Spot Junior, whatever. It's oval BA. And if we have time later, if somebody wants to ask me a question, I'll give you the history of these great white ovals on Jupiter because it's kind of neat. And about a month and a half ago, it turned red. It went from clear to red. And everybody got very excited. Christopher Go in the Philippines discovered it. And here, Dave Tyler imaged it. And it is like a little red spot. And he blew it up, and you can see it's got a little core. And it has details, and it has rotation. So we don't know exactly what's going to happen, but around July 7th, it's going to interact with the Great Red Spot, and we'll see what happens. It's probably kind of neat. There's the Hubble Space Telescope, and which is a whole lot better than Dave's. And again, it shows a nice detail inside that oval BA. So this is something we can all watch. And again, with the webcams and the new technology, why, no problem. This was a controversial image taken by Rolando Chavez. He was here at this meeting last year at the NEAC. A friend of mine in Atlanta, one of our avid ALPO observers, has features below the cloud deck on Titan. He did that with infrared. I mean, this is with I think he used a C-14 and a webcam. It's amazing, the stuff that is going on today. The image size, you want to figure out how big that image really is on your sensor. You got to, you know, do a few calculations. And literally, I do this when I go out and observe every night. And you figure the image size in millimeters or, you know, furlongs if you want, but whatever, it has to be all the same units. Image size is the apparent diameter of the object times the focal length divided by 206.265. Who knows what that number represents? That's right, it's the number of arc seconds in a radian. So if you're doing deep sky stuff, instead of using that number, you would use degrees, which is 57.3, right? Or 53.7, I can't remember. Yeah, 57.3. And that gives you the, let me give you an example here. There we go. Now, if Mars is 20 arc seconds, as it was this year, and I'm using an 8-inch f10, again, the old C8, so the effective focal length is 80 inches. I'm going to use inches instead of millimeters this time. And I worked that into the equation, and the image comes out to be 0.2 of a millimeter across. And so at my film plane of a C8, that would be what Mars would look like. Now, I don't care how fine grain or small pixels you got, you ain't going to get much out of that. Okay, so we got to do something. And this is the key to, again, the high resolution imaging. We have to increase the image size on the film plane or the sensor. And how you do that, well, there are a couple of ways. You increase the effective focal length is the only way, but there are a number of ways to get around that. One is mortgage the house, call you know, some friends I have over in the Middle East, and they can sell the wife and kids for you, and then you get one of these. Okay? Now this will look nice in your backyard, but I know the zoning regulations, so it's a problem. So there's other ways to do it. And there are really three basic ways to increase your effective focal length. One is negative projection, which is using a Barlow or a PowerMate. And here's reasons you do that. They're very simple. A lot of observers use this technique. They're lightweight. They're great with webcams and surveillance cameras. Here's a Teleview 4X, or 5X and the 4X PowerMates. I got these from Uncle Al a couple of years ago, and I have to confess they're too good to use with imaging, so I use them visually. I mean, these are good machines here. They really are. And I'm not, trying to sell these, but I do get a cut. So this is the simplest, most straightforward way to do high-resolution imaging. Another way is, especially if you have a digital camera, and Robert Reeves is going to be talking about this over the next several days, I think, Robert, about digital cameras. And a lot of them, the lenses don't come off, okay? So you got a problem there. You want to take a picture of a planet through that camera. Well, how do you do it? You use a thing called the afocal technique. And the way you do it is you get somebody like this. This is Tim Parker. He's from Jet Propulsion Lab. No relation. He won the Jerry Garcia lookalike contest a couple of years ago. And we're down the Florida Keys. This is my pride and joy, my little 6-inch f8 reflector. And Tim came over and he said, "Hey, Don," he said, "you mind if I use your telescope for a while?" I said, "No, that's fine. We're doing a Mars thing." And so he got a Nikon Coolpix, put it on a tripod, set the lens on the Coolpix at infinity, and then adjusted the focus with my telescope, which is the afocal technique. And he went click, 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 click like that, and then he went to the carport with his computer, and shortly later he got a picture like this of Mars. Now, again, 10 or 15 years ago, you would have published this in Astronomy Magazine without a question. I mean, this is a great picture, and it's only 24 frames stacked. So this is what you can do with it, afocal technique. You notice the camera wasn't even attached to the telescope. The telescope was driving, but I mean, you can do things like this very, very easily. And it's a nice way to, if you have a digital camera, jump into planetary imaging without spending a whole lot of money and effort. Okay, afocal projection, if you want to do some calculations on this, the camera lens you set at infinity, and the effective focal length is the scope's magnification times the focal length of the camera lens. So if you have 200 power and you're using on your camera, it's a 25 millimeter lens, you just multiply those together and your EFL comes out to 5,000 millimeters. And then you can calculate the image size and whatever. Or an easier way to do it is you put the camera up on the eyepiece and see how big the image looks. You don't really need to calculate this because you can always change it. But okay. Anyway, the technique I use and many people use is called eyepiece projection. And in this case, your eyepiece is actually a slide projector. It's like that thing up there. Then you have a projection distance, which is P here. The focal length of the eyepiece is the little f. And you can enlarge the image in a couple of ways. You can increase the projection distance, or you can double the power or increase the power of the eyepiece. And this little formula here, magnification factor, which is what you multiply your focal length by, is the projection distance divided by the eyepiece focal length minus 1. And of course, I can't remember why you get the minus 1, and I don't really want to go in. I noticed in the audience now I got a few deer in the headlights sort of. This is what I get when Richard starts going on about how to do this stuff. So I just write down, just do me what tell me what to do. But we won't be bothered with these formulas. But that's kind of the basic formula on how to calculate your eyepiece projection. If you really want to know, buy my book. It doesn't deal with CCD imaging. It's published in 1988, but it does have all the photographic principles you'd want to know, and all this stuff is in there. You just substitute for film plane, you put in pixel array, and you'll be all set. The number, of course, to get this is 1-800-825-STAR, or see Perry Vermaculis right outside there at Wilman Bell. The number again is 1-800-825-STAR. Just bought a new camera. I need the money. Okay. Now, eyepiece projection, we went through that little formula again. I'll just give a real quick example, and we'll get on to something that might be interesting. If I'm using a 25 millimeter focal length ocular, and the projection distance is 100 millimeters from the chip, I plug that into this little formula, I get a magnification factor of 3. Go back to our C8, and we have an F10 system, 3 times, which is a focal length of 80 inches, so 3 times 80 inches, 240 inches, and the focal ratio has gone up, 240 divided by 8, to F30. The focal ratio has gone up by a factor of 3. There's a surprise, the same as that number. So therefore, I know when I'm taking my exposure that for the 8-inch F10 at F30, I'm going to have 9 times more exposure, right? I've increased my focal ratio by a factor of 3. It's a square function, so hey, I increased my exposure by a factor of 9. It gets significant. And this is how you kind of match the image to the sensor, your focal ratio, when you sit down before you take an image and figure this stuff out. It really helps. Because then you don't wind up out at the telescope after you've assembled everything and say, oops, surprise, surprise. I got to take everything apart and change eyepieces or change my system. So it's just little helpful hints. And nothing is free in nature. Now, the eyepiece projection works nice because you can get really, really high magnification with it. It's versatile because you can put it in any eyepiece you want or can get. And it's really good for film or cameras with big pixels, which is some of the stuff I use. It does have some disadvantages, any of this high-resolution imaging. You get high magnifications with any of it. Well, that means it's hard to find the object, right? I mean, how many of you have got all your systems set up and there's no planet in the field, and you got to sit there like this with your finder, and then what do? You go out and get an auxiliary telescope, which I did at one time, a higher power scope, so I can center things. And I found really only one use for that telescope. And so I went to another system, and in addition to that, it was hard to find where the focus would be. And on these cameras, starting with the movie cameras all the way to the top-end S-big cameras, if you're a little bit out of focus, you don't see the image, right? I mean, it just blows up like that, and you look, it's gone. So you got to be approximate focus. So in addition to being able to find and center the object and get a rough focus, I use a flip mirror system, which I built. Actually, this one a friend of mine made. I Parkerized it. And it's just a little flip mirror in there. And you attach the camera on one end. This is an ST9. And the eyepiece goes in here. That's my projection distance. And I have a very low power eyepiece up there, so I can center. It's got crosshairs in it, and I can center the image. I can find focus, which will be approximately what the camera will see. So at least I get a running start on the focus. And it just gives an idea how the thing goes together. There's a little eyepiece down there. And I use very expensive eyepieces. These are $1,000 each. Somebody asked me at a talk one time, and I told them that, and then I said, ha, 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 it's not true. These are microfiche projection lenses. I pay $5 a piece for them. I got a whole drawer full of them. And just machine up a little adapter so they'll fit in my projection system, 1.25 inches or whatever. And I think they're available at Apogee and some of these places. Anyway, the guy who makes them was there with me, and when I said $1,000 a piece, everybody bought it. They all looked. And I said, oh, they're only $5. And he said, I could kill you. I would have split this with you. These people were ready, So I'm not a businessman. It's too bad. And this just shows the projection system hooked up to a telescope. And this is the most important piece of equipment you're going to have is a piece of string. It's called a lanyard. And it goes either somewhere where it's not going to fall off to something which will fall off, and that's your very expensive CCD system. And this is really important because this has fallen off. And the S-Big makes very robust cameras because it hit the concrete, and well, it's got a carpet. It still works. I was amazed. And because, I was expecting my wife, as Rob Gendler said, well, how much did we pay for that? That was going to be the next thing. Okay, and now we're going to get into a little bit about resolution, too. This is a big topic. And pixel size and pixel envy. Rule of thumb here is you take 205, multiply it by the pixel size in microns, divide by the focal length in millimeters, and that gives you your image scale. So if you have a 10 micron pixel CCD camera or webcam, your effective focal length is 8,000 millimeters, and that gives you about 1/4 of an arc second per pixel, which is pretty good. And that's about where, as a ballpark figure, I think for most amateur planetary imaging, that's a good place to start. Now, it's, again, no definite, this is not carved in stone. The Nyquist sampling theorem says that you need 2 pixel elements to form an image, and that would require or produce a resolution of about 1/2 an arc second. Well, I'm going to tell you right now, just throw all those ideas out. Because for Mars, first of all, we can oversample. And for many planets, we do oversample with the modern cameras. And I usually go about 1/10 of an arc second per pixel with Mars because it's small and has a real high surface brightness. And that's the other thing. Which planet has the highest surface brightness of any of them? Mercury. That's right. And we were at the eclipse down there in the Caribbean a few years ago. And I got a picture of Mercury and Jupiter at the totality, and Mercury is quite a bit brighter than Jupiter. Now, the reason you don't see it like that is because it's always very low in the murk, which is why it's called Mercury. Okay. Anyway, So at high focal lengths and high focal ratios, we can get shorter exposures with bright things if we oversample. Now, what about resolution? Everybody says, oh, resolution. The small pixels will give you better resolution. And was Dawes all wet? Well, the Dawes limit says that the resolution of a telescope is 4.56 divided by the aperture in inches. He was an Englishman, so we use English units. And this would mean that for my 16-inch telescope, maximum resolution I could get was about 0.3 of an arc second. Okay, well, here's Mars back in, I don't know, 97 or something. And these are real features. These are 0.16 arc seconds, 0.32 arc seconds. So we're already past the Dawes limit. And you have to remember that Dawes was a double sky observer, a double star observer, and he was talking about 2 bright points on a black background. And we're talking about lines and all kinds of different things, dark things against a bright background, specifically in planetary work. And Pickering, back around the turn of the century down in Jamaica, he said that the visual observer can surpass the Dawes limit by a factor of 14. And this is quite true. For visual observers, you'll see features that are just unbelievably small. So again, you don't get hampered down by these numbers. And the nice thing about this CCD astronomy is that, you know, if you mess up, hey, so what? You know, you haven't spent a fortune on film or anything, just go do it again, try something else. But here's Trishnicker, which has, I forgot what the smallest features are here, but they're in the 10th arc second area, again with a 16-inch scope. So, you know, you can do it with the CCDs, and you can produce decent images. Here's, you can get stuff near the Hubble quality. There's the Hubble, and that's me. And, you know, for $4 billion, it ain't too bad. I mean, they wouldn't pay that, but what the heck. And, you know, again, we're down in the 10th arc second resolution area. In fact, you notice how, you know, on Mars you get these dark Maria, you know, all the maps and everything show them real dark. Well, they're not. They're all a bunch of dots and stuff. And in 2003, it's the first time we really saw that the telescopes and the imaging was good enough to actually see what some of the great observers like Bernard back 70 years ago saw with these big refractors in moments of really good seeing. They said, oh, those dark areas aren't solid. They're all, you know, a bunch of dots and stuff. And so, I mean, we were getting the resolution now of 40-inch telescopes all of a sudden with amateur scopes. So it's kind of neat. So anyway, I tell you to ignore Nyquist, ignore Dawes. Not really, but you know, they're good starting points. Because really, we're talking about resolution. Well, imaging is not about resolution, or not just about resolution. Very, very important is a thing called contrast. You know, you see things by contrast, in addition to how you can resolve them. And the combination of the two, resolution plus contrast, is something called the modulation transfer factor. Richard would be much better at talking about this than I, because I always forget it. But basically what it is, it says that if you take an object here, which you can see dark lines or you can see bright lines, depending on, you know, whatever, and you put it through an optical system, and in this case that achromatic lens represents the Earth's atmosphere, the telescope, the dirt, filters, various things until it gets to your chip, it's going to be degraded, okay? If it were a perfect system, this would look exactly, these two things would be exactly alike. But what's happened is that we have lost contrast as we've gone from here to here. We've gone to a sine wave, and we lose 80% contrast. Now, these features are pretty far apart, and these are called low spatial frequency features, which means like the big belts on Jupiter, big blobs, dark things. And then if you go to a high spatial frequency, you notice the degradation is much more. Okay, now our job in planetary imaging and image processing is to try to resurrect this, try to salvage this image to get it something back to the original. Modulation transfer of 1.0 would be this equals this. Well, this obviously doesn't. This is much lower. And we use this because it's an optical test people use in the lab all the time. And just the reason I'm telling you this is I had to take a certain amount of time for the talk, and I needed fillers. And this is one of them, because I really could care less. But anyway, this is things that will give you a poor modulation transfer function. Well, poor optics, you know, duh, and a bad figure. Okay, but you know what's more important, I think, than most of this stuff on here is rough optical surfaces. And I've become more and more, you know, attuned to the fact that if you have a really, really, really smooth optical surface, it makes up for a whole lot of other problems. not poor focus, but a whole lot of other problems. I remember looking through an 8-inch F8 or 6-inch F8 spherical mirror telescope made by the Russians, and of course made by the Russians, it weighed about 2 tons, you know, this monstrous thing. And the images in it were quite good. Now you got to parabolize a 6-inch F8, and this was a spherical mirror. But when I looked at it in the focal, I mean, it was absolutely perfectly spherical, and it was absolutely perfectly smooth. And I've got a Muon 10-inch now, which breaks all the rules. It's got a big central obstruction. It's got a 3-vein spider. It just goes against all my things I've been preaching about over the years. And again, those surfaces are so smooth. The images are wonderful. So this is very important. And, you know, everybody talks about figure and you know, laser interferometry and all this sort of thing, and peak to valley, and that's fine. But really, you want smoothness in your figure, and that's very, very important in telescopes. Oops. Now, how do I go back? This is going to be a problem. Oh, no, it isn't. Sorry, guys. Should have stuck with what I know. I'm also hampered by the fact that I can't see anymore. Okay. Yay, we did it. Yay. Okay. Dirty optics, of course. Although, again, you quote Alvin Clark when he had a little defect in one of his magnificent lenses, and he said, well, optics are for looking through and not at. So, I mean, some people go a little crazy on cleaning things, but basically, you don't want dirty optics because they cause light scattering. Bad seeing, we can't help that. To some extent, we can by, you know, moving to a good place, but bad seeing, poor focus, anything that increases your diffraction, like, you know, the cat who's sleeping inside your tube, maybe, or laying on your telescope mirror, that would be poor. Big central obstruction, we all know the arguments about that. And the thing really gets me is poor collimation. And this just shows, this is from an article in Sky and Telescope in the June issue, I believe. And it's also taken from Dick Suter's book, which is available at 1-800-825. Thank you. Okay, this again shows the modulation transfer, one being perfect. You know, you have absolute perfect transfer. And this is the frequency increases. In other words, we're getting the high spatial frequency out here, where you're really going to have a problem converting it. And it just shows a collimation of 3 minutes of arc. Okay, on your telescope will produce, or 6 minutes of arc will really mess up the image. So every night before I observe, I collimate. Now, a lot of times I don't need to, but it's nice to know. And with a big heavy mirror, and I know a lot of your Schmidt-Cassegrain people, I owned one for a long time, and every time it moved a different part of the sky, I'd have to recollimate it. And but it is very, very important to do this. Otherwise, you're going to get image degradation. Either telescope is collimated or it's not. Okay, there's no such thing. Hey, that's good enough for amateurs. You know, I mean, it's either going to be collimated or it's not, and it does require some effort. That 3 arc minute thing on that previous graph, on the telescope they used in that example, the amount of error that you could detect in the collimation with a laser collimator would be smaller than the hole in the laser collimator. So that's the other thing I have. I have a laser collimator which I got from Howie Glatter at the Winter Star Party. It's a really beautiful instrument. And I haven't used it yet because Tippy Diori is supposed to come to my house and teach me. But one thing we know about laser collimation, it's really good for getting the optics generally squared and getting your focuser squared off and the diagonal in proper position. But when it comes to really the nitty-gritty in collimation, you're going to have to go on a star. Okay, and that's kind of what, you know, as a rule of thumb, and I do this every night. I also use very delicate instruments when I go to collimation. It's a delicate procedure. And I get a star on the telescope, and you go outside of focus, and there's the image of your secondary mirror, shadow of it, and everything is concentric, and that's the way it should be. And you go in focus, that's the airy disk, and these are the real diffraction rings around the star, and that's the way it should look. And very often you'll see a situation where outside focus, yeah, it's close, and it's really hard to judge. What you do, and the real critical thing is you go in focus. You make your collimation adjustments, you go in a little bit, keep going in until you're at focus, and yeah, you say, you know, that's really not very good. The diffraction rings are on one side. So fixing that is easy. You just move the adjustment so that the airy disk goes in the direction of where it's lopsided, and it'll eventually come out fine. This required very small adjustments, but still it's worth it. And I take up to half an hour sometimes, because I'm an obsessive compulsive, but you know, it is important. Now notice I say outside of focus here. If you check collimation going inside focus, frequently your focus tube, your eyepiece tube cuts off some of the light from the mirror, and all of a sudden it will look collimated. So you get quite a different view that way. So I always go outside focus. Okay, and that was only 5 minutes off, by the way. 5 minutes of arc, which is, you know, pretty good. There are other problems you get with, you know, degradation of your modulation transfer function. This picture I took the other night of Jupiter, and we have here, the mirror is not cooled, and we have tube currents. Now, I use fans on my mirror. We have a bad case of tube currents here. Anyway, I use fans, and I used to think that was to create laminar flow going up the telescope. And it's not really. What it is you're cooling my mirror down. Now, in Miami, at night the temperature plummets, maybe 3 or 4 degrees, you know. No, it may go down to 80 degrees sometimes. And it's not like you guys up here have it where, you know, you can talk 30 or 40 degrees where you're really continuously fighting this. But basically, you want the mirror cool down to ambient temperature, and you want to, you know, have enough space around the tube, inside of the tube, so that you aren't bothered with currents that creep along the tube and all that. So these are kind of important things. I leave the fans on usually when I image. Some nights it's better when I take them off. I can't tell you why, but most of it has to do with the temperature on the mirror, I think. Alan Adler out in California, you've probably seen his articles where he blows fans directly onto the mirror because there's a boundary layer of turbulent air right on the surface of the mirror, and it blows that off and the images improve. And I just haven't had the courage to do that, primarily because I live in a very salt environment, and I have enough trouble keeping my mirror clean without blowing stuff onto it. So it's a good idea, though. Okay, let's go a little bit on camera types. Okay, there are two basic types, cooled CCD cameras and webcams, representing the cooled, the S-Bigs, the Starlight Express, the Apogee, the Finger Lake instruments. And these have certain advantages. They're very low noise. They have a high dynamic range. You know, the grayscale can be enormous on these things. They have a high bit depth, which means they're very sensitive. They're photometric and quantitative, which is really important. I really feel webcams are not that quantitative. They're really great, and you get a lot of good stuff for amateurs to produce in them, but they're not that quantitative. So here we have a much better shot at being quantitative and really providing accurate color information. Now, these are all monochrome cameras. They're black and white. But you can put specific filters in them. They will record faithfully what passed through that filter in a linear fashion. And the professionals really like this data. And a lot of the stuff we do goes to professional astronomers, because in planetary work, the planets are always changing, and the pros can't keep up with it. And if there's no spacecraft at a planet at that particular time, why, we get the job of helping out. So that's kind of important. And these are low noise enough that the images may not need stacking. Here's, I took this single image with the ST9XE at 20 micron pixels, big pixels. And this shows you the color composite I did. This is the red, which are, you know, 2 images stacked, green, 2 images stacked, blue. Well, I got 3 images because they're a little noisier. And you pop them together. Now this is really better than, you know, stacking 2,000 images, because you can pick the really sharp ones and put them in, and you get a little bit better deal on the thing. So this is one of the big advantages. That was taken at f60. I can use f60 because the camera has big pixels. It's very sensitive. And the sensitivity of the f60 was offset by the increased sensitivity of the camera. There's a picture of my telescope. It looks horrible, doesn't it? Love it. Anyway, I got the ST9 sitting up there, and I'm dealing with a large optical system with big aperture, so I can use higher focal ratios because I'm pulling in more light and have a very sensitive camera. Now, these cameras have high dynamic range, and that's one of the things you should look for in a camera. That's the full well depth divided by the readout noise gives you the dynamic range. And in the case of the ST9, 180,000 electrons is the full well depth. That's how many electrons go into a pixel, I guess. You divide that by the readout noise, which they tell you is 13 electrons, and you get a number that says 140 or 14,000. And do a little math, it's close to 14 bits. Now, all these cameras are advertised as 16-bit, right? Well, that's true. The A to D converters, the analog to digital converters of hardware is true 16-bit. The camera's not. They don't tell you that little detail. So it's kind of nice to know what the dynamic range is. What dynamic range means is that you've got a much larger selection of grayscale values to pick from. And you can pick out some of the fine details, and that's particularly important for deep sky work where you're dealing with very faint details in nebulosity and galaxies. Okay, disadvantages, they cost a lot of money, they're heavy, but I have gone along with that. Having had numerous knee operations, I own a large selection of these Velcro bean bags that you put around your ankles, weights. And so when I put a heavy thing on there, I just slop some on the Velcro on the telescope, which really enhances the ambiance of the instrument, I think. You know, it makes it look nicer. Anyway, it's a quick and dirty way to do it. And I would suggest if you have neighbors that are into jogging, you just go out in the morning with your telescope and let them look through it, because when, not if, but when they have orthopedic surgery, they can give you some of their ankle weights. It's very helpful. Okay, the cool CCD cameras require a fairly extensive setup. The wiring, typical of one of these. And, you know, it gets to be a little troublesome sometimes getting the wires. Older cameras have slow download times. You have to get a USB hookup or FireWire, something that'll give you very fast readouts, because otherwise, you know, you're always changing focus, you're always changing things on planetary imaging. And if you have a camera that takes, you know, 2 minutes to download the image, you're just not in the right place. You can also subframe most of these cameras, which is nice. And these cameras do require, again, Rob alluded to this this morning, fairly complex, expensive software. Now, this is what I used for that Mars image I showed you a few minutes ago. I used 4 programs. I probably used more. I just can't remember. I've repressed this. And AIP for Windows is fairly inexpensive. I don't know what they're charging for it, but it's a pretty good price out there. Maxim and Photoshop are very expensive, okay? CCD soft is free if you buy a Paramount. So, you know, we're talking some expensive stuff here. That's a good deal. And I put a total of 4 to 6 hours of processing in. I was complaining about this to Ed Grafton in Texas one time, and he says, yeah, I do 5 hours myself. It takes a long time to do this. And with webcams, you don't have that problem. It's like getting a root canal. You know, it's nothing I really look forward to. So we go to the next thing. The last thing is these webcams. Now, they have a number of really great advantages, and I really feel that they've revolutionized amateur planetary astronomy. They're just unbelievably neat little devices. I belong to the Association of Lunar Planetary Observers. We have a Mars section that every year we collect images from observers around the world. And this year, in 2005, we had 6,000 observations from, Romania, Slovenia, all these countries you never heard of, really. And these guys were little 6-inch telescopes there and doing beautiful, beautiful images. And 95% of the images we got were with webcams. And this stuff was really, really good. By comparison, in 1988, when Mars was almost as close as it was in 2003, it was a great apparition. It was higher up in the sky. We got 2,700 observations. Of those, well, you remember that, Eric? Great apparition, but you know, a lot of those were drawings. Maybe half of them were photographs, and certainly no CCD images, because we didn't have those in those days. And the quality was less, the coverage was less. We thought it was great at the time, but now, you know, average apparition we get is 6,000 or so, and this is ho-hum. I do have to put a little plug in for the Association of Lunar and Planetary Observers, which I'm a member, and it's a nice organization. They work us like dogs, but it's really devoted. And, you know, I'd ask you to go on our webpage, Google ALPO, and when you get through with the dog food stuff, you'll see Association of Lunar and Planetary Observers on there. Check out our website, and we work very closely. We have a very active board of directors, and we work with professional advisors who've been a tremendous help to us. And quite literally, we'll always get requests to image this, to image that, and these guys take their time. Sanjay LeMay is one. We've had the guys who worked, the guys who are doing the Pathfinder, the Opportunity landers. They've been helping us, and they're all a nice bunch. And basically, planetary astronomers are not really stuck up. They're nice guys. They drink scotch. They're on the bottom of the totem pole as far as astronomy goes. They know it. And so, you know, they use the amateurs a lot. And remember, there's no spacecraft at Jupiter now. There won't be for quite some time, so it's ours again. Now they know our names again. You know, it's kind of neat. Anyway, enough of the ad. Advantages, these webcams are relatively inexpensive, although that's going up. You know, the 2U camera originally was, what, $75, now it's $140. And, you know, the Luminera is up $900 or so. So, but they are very lightweight, they're easy to use, they're easy to set up. And the nice thing I like, you get fast results in real time. And they're portable. This I took out in the Everglades, out in the middle of a swamp where the sheriff came by. What you boys doing there? I mean, really, it was like a Jackie Gleason movie. And we had working out of the back of my Explorer with a laptop computer and a motorcycle battery driving a little 6-inch scope. We got this nice little thing here. So you can do all kinds of nifty stuff with these webcams. Good thing, the processing software. Remember I showed you those other software, you got to buy a Paramount first? And that's no. This is free. And K3 CCD tools, you can get these on the internet. That's no longer free, but it's $20. We use that to run the cameras. And again, Robert's going to be going more into, you know, how to run these cameras. And Registax, which is what we use to process the things. I'll be talking about this afternoon. Stuff's free, and it's really good. So this is a big advantage, and one of the reasons people use webcams. Now, in addition to being free, what I like here is you get one-stop results. Okay, I don't have to, you know, go 5 hours of processing. I don't have to go to a photo store to get these things done. There's a picture of Jupiter I took a couple years ago, and I just loaded the image, the AVI file here, and that's one frame, raw frame, okay? I plop in the Registax, and I'm lazy, so I generally just let it do its own thing, figure it out, and I come back in about 10 minutes, whatever, and there's my picture, okay? And the processing I did, I moved this slider about halfway up, and that was it. So this is really a nice deal. You can, of course, I had very good seeing that night, but with a webcam, you get fast results, and you can see also if you messed up and go back and do it again, usually while your telescope is still set up. I'm going to show you some kind of interesting stuff here. There's a program called GIF Movie Gear, and you can get it at www.gifmoviegear.com. It costs, you get a 30-day trial, and it costs $39 if you buy it, and which I did immediately because when asteroid NY40, 2002 NY40 came near the Earth, I had a 3-inch refractor hooked onto my 16. It was one of these, you know, really cheap refractors, and I stuck my ST9 on there, and I got all these neat images, but I wanted to make a movie. And I went to CompUSA, and they said, yeah, for $2,000, we'll sell you this special deal. And then the owner of the store comes up and says, you know, GIF Movie Gear. So I went home, put it in. I put in the JPEGs. All I did is open the JPEGs, and hopefully, there it is. And that was it. Made a movie for me. And, you know, I'm not a computer guru, and this is really wonderful stuff. So one of the things you can do in making movies, in addition to being aesthetically pleasing, is you can get a lot of detail that you might have missed in the still pictures. Here's just showing some of the stuff I've done with Jupiter rotating and the moon's going across, you know, eclipses. You can do, again, with webcams. It's so easy, it's much easier than with the cool CCD cameras, because to produce the full rotation of Jupiter, I'd be there for a week processing all these thousands of images. With a webcam, I just tell Registax, go ahead and do it, and I get a whole series of images like that. But again, you can make discoveries with this. This is a little spot on Saturn. See it right there? Rotating, and some spots down here too. And now, this proves the virtue of being a really selfish SOB. The night I took this, when was it? Oh, January 24th. I was imaging Mars, and I was about to close up, and my wife comes and said, oh, could you watch our granddaughter for a while? I have to go do something. And I said, no, I really can't because I got to image Saturn. I just bought the Luminera here, see, and I was testing it out. Now, I don't like to image Saturn. Nothing ever happens on Saturn, right? You know, every 14 and a half years, I turn the images upside down and send them back in. So, but I had to image Saturn that night, see? So I took some pictures of Saturn, and I saw these little spots. And I said, well, I'll take some more. You know, it's over about a 3-hour period. I took these images, and I put them together in a little movie, and sure enough, you know, there were spots. So that was kind of nice, and so I sent them into the ALPO guy. And since I never get my email, you know, at the end of the month, I get it whether I need to or not. There was an email in there from a professional astronomer at JPL who said, yikes, the Cassini spacecraft today, on the 24th, has just witnessed the biggest electrostatic discharge I've ever seen on Saturn. You know, to translate, it's a big lightning storm. And this was it. And I got one of the first images. Actually, a couple of French guys beat me out by an hour or two. But basically, you know, it was a discovery. It was kind of neat. And this thing has actually lasted for about 2 months, at least. So, again, you know, if you can be a real selfish guy and don't babysit your grandchildren, you can do stuff like this. I think it's, you know, it's very nice. Basically what I'm saying is that you just keep shooting, you just keep imaging, you're going to discover something, because the solar system is always changing and always got surprises. A guy up in Canada, Rolf Meyer, did this little 4-day sequence of a dust storm exploding on Mars. That's the start, and you know, you can just see 4 days how it is. And again, you can really see this dramatically with videos. This is a cloud on Mars called Arsia Mons. This is a big cloud seen over one of the volcanoes, and as evening approaches, it gets brighter and brighter. Look at that now. You'll see here, it gets brighter, bigger, brighter, just like they do in the south and the Rocky Mountains of the afternoons, summer afternoons. And you can, again, show that very, very nicely in videos. I hate this guy, too. I don't know where Adrian Jones is, where he's from. He's got a very small telescope, and he imaged Phobos and Deimos this year with a webcam. I think it was a 2U cam, very small telescope. And then to make me feel really bad, he made a little video of it. That's over 30 minutes showing him how they move. Isn't that cool? Again, this is fun stuff, and it's also very useful stuff. This is occultations. You know, you can do those all the time. That's Jupiter and the moon. And again, just showing, you know, it's nice for kids too. You know, you go to schools or you get your grandchildren and show them this stuff, and it makes it come alive. So the big advantages of the webcam. I mean, they're cheap, they're noisy, they're all kinds of other things. But they have very high sampling rates, fast integration times. Now, with a CCD camera, we're talking 1/10 of a second, 2/10 of a second, you know, real fast. With webcams, you can go to 60th or a 90th of a second now. And you know, even with the very inexpensive ones, you're going frame rates of 10 times a second. So this, you really are in a position to beat the seeing. And again, I just bring that graph up to show how the exposure times have decreased. We call them integration times because you know, I'm a retired physician, and you just don't come out and say something. You have to say something that will confuse people, so you make up new words. And integration time is a lot better than exposures. So, you know, what the hell is he talking about? It must be expensive. Okay, now I don't know if I can do this. I'm going to try, but with this setup, I just want to give you an example, I hope. Maybe not. Oh, God, okay. Well, I was going to get, oh, there it is. No, that wasn't it. I actually had an AVI frame I was going to run in there, but it won't do it. And it was an example of really awful seeing, and that was the result I got with a webcam, so we'll just carry on. Disadvantages, webcams have a lot of noise, and you need to stack the images. And one of nice thing for us is that the signal increases with the number of images you take. The longer the exposure, the more the signal. And the noise increases as a square root of the number of exposures or the time of exposure. So you need to stack the images, and the more images you stack, or the longer your exposure times, you increase the signal-to-noise ratio. Now, deep sky guys just increase, you know, they just expose for longer times. We can't in planetary astronomy because we want to get it down to beat the seeing. So we use short exposures, but we stack a whole lot of them, and we generally improve the signal-to-noise ratio a great deal. Stack 9 images, signal goes up 9 times, noise only goes up 3 times, so you get a 3 times better S-N ratio, which is kind of cool. Now, just getting in a few words on taking the picture, and this afternoon we can talk a little more about this. First of all, center and orient the picture, the image, and focus. We'll talk about that this afternoon. I got handed this thing about an hour ago on would you give a talk. You do it a lot. Okay, that's my talk on focus. You don't have to come. And because, you know, you're remember, again, Rob this morning said that, you know, the mirror cools, your optics cool, the focus changes over the night. Okay, it changes from, you know, maybe 10-minute period to 10-minute period. Because even in Florida, I'm talking a 100th of a degree change in the temperature. When you're shooting at f60, that's a big focus change. Okay, maybe 1,000th of an inch. So you have to check the focus a lot, and I check it on the planet. And I really totally recommend electric focusers. This is my nice-looking telescope. I've got one of these Starlight focusers, fine focus things, which are great for Newtonians, but for Schmidt gases, they tend to slide out. And I have a RoboFocus hooked up to it. And this afternoon, I'll tell you, if you own a milling machine and a lathe, this works real well. But some of the stuff you buy off the shelf, and they're going to do that some problems. This is a very important piece of equipment when you're using heavy devices. It's a rod with a turnbuckle. So it keeps everything sort of square, okay? Another fancy thing that sells for $2,000. Taking the picture, set the exposure. Okay, generally for the planets, you're going 50 to 75% of your full well depth maximum exposure value. If you're using a 16-bit A to D converter, your maximum full well depth is 65,000 whatever ADU. So you don't want to go 65,000 ADU for your Mars pictures because you'll burn out everything. And generally you go 50 to 75%. Now fortunately, the programs we use have histograms attached, and this is a picture, real thing of Mars. And here I'm at 44,000 ADU, which is what, 65% of the full well depth. And this is what you want to go on, and it really helps you determine what exposures. K3 CCD tools with a 2U cam, it's got a little meter there. See, about 50%. And that kind of, it also gives you an idea if you messed up and you knew what it was before, and you can change it. And this is with the Luminera. Again, it has a plug-in, which is a levels meter, which is a tremendous help. So, exposures, if they're too short, you get noise. If they're too long, you burn out details. And how many pictures of Jupiter we've seen, including my own, with the equatorial zone just blotted out because the exposure was too long. And when you stack images, you know, they burn out more. So you have to be very careful and don't overexpose. And some webcams, unfortunately, and again, Robert will get into more of this, they need high gain. Just counterintuitive. 2U cam and the ATEC 2C, if the gain is too low, you get these really neat little lines off here. I call them isobars. And many, many images we see those. Okay, the way you solve this is you increase your shutter speed, which is great, go from a 25th to a 33rd of a second, and you run the gain up. You say, well, you're getting more noise. Okay, you're getting more noise. You're stacking 2,000 images. I mean, what the heck? And it'll get rid of some of these artifacts in here. So artifacts is something we always have to worry about. Now, we do have some pitfalls. I'll just spend a couple of minutes, and then we'll go for questions or whatever. There are pitfalls. You know, everything's going well, and all of a sudden something bad happens. And that is in my observatory, by the way. That was real. That photograph recently appeared in a Dutch astronomy journal, as a matter of fact. So, anyway, one of the pitfalls is that you don't have the date and the time. You know, we get images submitted to Alpo with no date and time on them, or if it is on them, it's wrong. Now, so what you do is, first of all, you make sure your computer is set to the right date and time. And I use this little freeware called Atomic Clock, and it comes up whenever I go online. I ping, and it sets the thing to UTC, and it allows for, you know, light time and satellite light travel and all that sort of thing. So it's accurate down to at least a second, which is good enough for us, and it's really accurate to better than that. So make sure before you start, and that's especially true now with Jupiter and Saturn because they rotate so fast. So you need to put the accurate times. And then when you save the images, these are the AVI files of a run I did on the 21st. You know, they have the times on there, and it's universal time. That's what we use is universal time. And I make a little file of that, and I actually print it out on my inkjet printer, and I store it. So I have a record of what time these images were taken. And remember, that's the time they were saved to disk. Not the, I messed this up badly this year, not the time that they were actually started. Because to give the time on the image itself, you have to kind of go halfway, you know, whatever your exposure time. You go 60 seconds, you have to subtract 30 seconds from it. But make sure your date and time are accurate. And time constraints are important because the planets rotate. And here we see, you know, Jupiter and Saturn, you've got really about 2 minutes maximum before you start getting smearing. Mars, 5 minutes, and of course deep sky was no problem. As Rob said, you come back next year and do it again. Okay, one pitfall is compression. Most programs have a little thing hidden away on your webcams. Will give you a thing about compression. They'll say no recompression. It gives you a whole series of little menu items. It's hard to find. You've got to look for it. And basically what you want to do is, it's under settings usually, compress, and you go full frame uncompressed, okay? Because when those images are going down that USB cable, you don't want them compressed like JPEGs or whatever. You want them, all the information there. And that's the problem with frame rates on these cameras. If you go above 10 frames a second on a USB 1 system, you're not going to drop images. What the computer is going to do is saying, well, this is a backlog here. I'm just going to kind of, you know, figure out what this image would be like. We'll make it like a JPEG and make it a lossy image, and so that stuff goes in and you lose information without knowing it. And that's when you get a lot of these artifacts and strange lines and things on the images. So it's important to make sure your full frames uncompressed And I just mentioned about the frame rate being too high, USB 1, 5 to 10 frames, USM, USB 2, 60 to 90 frames a second. We're getting up into that realm now, which is amazing. But, and FireWires are also very similar frame rate, very fast. We use color webcams a lot, and we have a problem called prismatic dispersion, which is the Earth's atmosphere. The lower the object, the more the dispersion. This is what causes the green flash when the sun sets, and you got a blue on one side and red on the other. And you can get around this by putting wedge prisms into your optical system, which of course, you know, you're losing light by putting more optical elements in. Adirondack sells one of these, and I bought one. It works great. You just rotate the thing until the prismatic dispersion goes away on your screen. Now, the problem is, as the planet rises, it changes, and you've got to have to keep rotating. The other problem is that every time you rotate it, remember these are wedge prisms, the image goes flying off your screen. You know, you got to get it back, see? So I did that for a couple of days and tried to sell it. Nobody wanted it. It's a good piece of equipment, really. But so then I went and I said, oh, I got Photoshop, and I got my channels here, and I got red, green, and blue, and I just blink them back and forth, and I move them, and I wound up with that. Okay, it's saved me the $240 that I would have spent for that thing. One a little helpful, this little icon up here, you got to click on that before you move the image. Oh, Photoshop, that's crawling through a minefield, that program. You know, these guys are sick. They're sick, demented people. And, you know, they got all these little things in there. You know, how many programs you have that doesn't have an open icon? No, Photoshop, you got to go file open every time, see? It's a little joke these guys play on you. But anyway, just remember to click on that thing before you move the image. And we'll be talking a lot about Photoshop this afternoon. Alan Adler sent me this. He did this in, I think, either Registax or Photoshop. Just combined the red and the blue, got rid of the prismatic dispersion. Stray light reflections. Is this Saturn? I'm not familiar with Deep Sky. But anyway, this is, you know, a really crummy picture. This is one of my few efforts at Deep Sky. And it's you know, I called Brian Marsden at the Cambridge, and I said, hey, I discovered a new nebula. And it's right near the dumbbell. And then I found out that this is the back end of my telescope, and I've got a green carpet, which, by the way, came from the original Dolphin Stadium when they went to AstroTurf. This is, you know, a collector's item. And inside my observatory, there's a door. I keep my computers in there, and I got a little 25-watt light bulb on the ceiling, which doesn't shine on the telescope, but the light kind of bounces on this green carpet and went up the end of the telescope and caused that fogging. So I just put a piece of wood back there to block it, and it got much better. Some of these cameras are, you know, they're sensitive as heck, and you really got to be careful about things like stray light. This is one of my better flat fields. This is with the ST9. I said, you know, this probably isn't right. I mean, my images aren't that good, but it ain't like this. So what this was the adapter tube I had, the 1¼ inch adapter tube they had bored spiral grooves inside it. Actually, they were raised a little spiral. It was like a spring being inside the thing to cut off stray light. Well, what it did, it bounced the stray light right back into my camera. So I, you know, being a machinist, I got a baffle. I made one. Took a fiber washer and drilled a hole in it and stuck it in there. I mean, I was imaging that night, and I couldn't go down and machine something fancy, and did it out, and there's my flat field there. So this is important to always check your flat fields, because that tells you a whole lot about what your optical system is doing. I got a UV filter for Venus that did the same thing. I went crazy. You know, I got 2 Venuses here, and that was why.
Sure that's not a transit of Venus right
Right there. No, yes, it is. No, I'm glad you asked. That is dust. And how do you get rid of dust on a CCD chip? Anybody here find it easy? How many find it hard to get rid of dust on a CCD chip? Right. Okay. Now, there's the best way to do it, short of blasting. I mean, I was getting to that. You know, just get to dynamite. A thing called Static Master, and it costs about $20, $25. You get a Photoshop, or if you get online, you got to buy 3 of them minimum. So I didn't do that. It has radioactive plutonium. Oh no, polonium. That's right. And all you have to do is pass it over that CCD chip and then use your blower, and the stuff comes right off. Because the reason that stuff's so hard to get off is electrostatic charges on there. And man, they, you know, electrostatic force is a really, really powerful force, and we prove that with these things. So get one of these little brushes and just destaticize the little dust particles on there. It works out fine. If you have big donut-looking things, those are not on a chip. Those are on dust particles or globs on your filters or somewhere away from the chip, and those generally aren't that much of a concern. Those can be removed with flat fielding. If you flat field out the little things that are on the chip, they come out, but then when you unsharp mask or process them, they come back in spades. So those have to go. We'll get rid of those. Image processing we're going to talk about this afternoon, and that's about all I have to say, except Richard isn't here, unfortunately. He always called this the digital dark room. There's my dark room, so I'm really happy to get rid of that place. And it's too bad. He introduced me, and I had this all set for him. Geez. Yeah, anyway, that's Richard. When, you all heard the story of how we started in CCD astronomy and everything. One thing you don't know about Richard, you'll be giving a talk this afternoon. The guy is one of the most inventive guys I know. Now, these CCD cameras were great. Back even before he came with his little computer to process them, we knew we could get images with them. We just didn't have any way to process the things. And there was a guy, Steve Larson, at the University of Arizona, took some of my Mars photographs, essentially did what Richard did. He photographed them with a professional CCD camera. This is 1988. And then he did an image processing algorithm, and they came out, my God, I could almost see craters. It was unbelievable. So I called Steve on the phone. I thanked him. I said, could you tell me how you did that? So he sent me his algorithm. Now, if you're a PhD in math and calculus, I guess it's totally incomprehensible. Not today, but in those days it was. And very few professionals or amateurs could do this. Until Richard came along and he figured it out, and he did AIP for, it's called batch picks and color picks and all these simple little DOS programs. DOS is something, we'll talk about that later. Anyway, did these little programs for these very slow computers we had at that time, and we produced really great images with them. So Richard is very inventive, and which reminds me, of course, we went to an annular eclipse in Kankakee, Illinois, and there he is, and we're clowning around. He's got his little Dobsonian there, and we discovered that, hey, we don't have another piece of cardboard. When the totality came to block out the sun on the thing we were projecting onto, we needed another piece of cardboard. So Richard said, hey, don't worry. We called this bald guy over, and it worked great. Except, after about 2 minutes, he kept saying, it's getting hot. We wouldn't let him leave, Anyway, so go out and try to image the planets. I think you'll really enjoy it. First of all, it's fun. Things are always different on the planets and even the moon, and I think you'll enjoy it. You'll have fun. And, you'll make unexpected discoveries. Imaging the planets is kind of like going out to a Chinese restaurant. You never know really what you're going to get. So. Okay, thank you.